Hey, good morning, team. Chemistry Coach coming back at you again. We're looking at orbitals today, not Bohr orbits. We're not talking about those circles where you got a point particle of an electron moving around with quantized angular momentum. No, 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 no. We're looking at these solutions to Schrodinger's equation. So, if you need to review that last video, that was a tough one, right? On the wave mechanical model. That was a doozer. Boy, I left a lot out of that as well. A lot of the math we left out. I'm going to do the same thing. I want to look at what are these solutions to Schrodinger's equations, right? What do they look like? What do we get, right? So we mentioned that the solutions are orbitals, but I want to look at the shapes of these, how the mathematics, you don't need to know the mathematics. I'll put up kind of a summarized version of the solution to Schrodinger's equation so you can sort of see how the math works and, why do you get a node there? Why do you get a region of zero electron density at that point? Why do you get a sphere there or a circle there? Why is this one bigger than that one? Those kinds of things. We'll just kind of briefly look at it mathematically, but really all you need to get out of this is what are the shapes of the different orbitals? Good. You probably looked at those in introductory chemistry, but I want to, let's open the rabbit hole a little bit more, my friends, and go, yuck, I don't like that. But anyway, I'm going to put it up whether you like it or not. So here we go. So just a review of wave mechanical model. So the wave functions, when you solve Schrodinger's equation, when Schrodinger solves Schrodinger's equations for hydrogen or hydrogen-like species, one electron species, we haven't done multi-electron species yet. That's going to be later. Those solutions are wave functions. You get a wave function that represents mathematically that electron's motion, and we can get the energy out of that as well. So they're mathematical solutions to Schrodinger's equation. Yikes! All right, and again, you get a three-dimensional image when you plot it. You get, remember in polar coordinates, you've got the radius, you got this angle theta from the z-axis, and you've got this angle, phi, fo fum, whatever it is, right, on the xy plane. So you got these two angles in polar coordinates and a radius that can tell you where this particle is, right, if you think of it classically. So, but if you square the wave function, you get the three-dimensional electron probability distribution. Some people say the electron charge distribution or charge density distribution. The highest likelihood of where this electron's going to be. Remember that electron's spread out, thank you Heisenberg, negative charge. And then because it's hard to really define the surface of an orbital, like defining where the atmosphere ends, kind of hard. Where, is there a specific, nanometer where the atmosphere becomes space? I don't know. It just kind of blends into it. I guess we could define one, right? So same thing with an orbital. We're going to take this electron density distribution, the probability, and just say, hey, you know what? If we draw a line right there, that contains 95% of all the electron probability. There's a 95% chance that electron's in there. Some people do 90% surfaces, whatever. So we'll just do 95% just to make sure, all right? And that's what is defined as an orbital. Okay, let's look at orbital sublevel and orbital notation. That's going to lead us, ultimately all of this is going to lead us to electron configurations. Where are the electrons in what electron seats or orbitals? We want to know where they're at, and that we can predict some chemistry from that. So let's look real quick at sublevel or subshell notation, where you have N and L, and let's look at orbital notation as well, where we have the M sub L values, which is going to be our focus for the shapes. It's a hot one today. I'm sweating, guys. Woo! Southern California in the summer. Yay! All right. So real quick, we're going to see this when we do electron configurations later, so you're probably familiar with this. But when you're notating a specific subshell, right? Well, there's two quantum numbers that designate a subshell. The principal quantum number, N, right? And then the angular momentum quantum number, L. Now remember the values of L. 1, 0, 1, 2, 3, those kinds of things. And we use letter designations. So for L equals 0, that's called an S subshell. L equals 1 is a P subshell. L equals 2 is a D subshell. And L equals 3 is an F. The traditional or notorious, depending I think of it, SPDF notation. Oh, we're going to get a lot of that till we have nightmares. So what we do is we just take the principal quantum number, n, so that could be any integer greater than or equal to 1. So it's going to be a 1 or a 2 or a 3, 4, 5, all the way up to infinity, which would be the electron popped off, right? So we just write that number. And then next to it, we write the angular momentum quantum number, L. But we're not going to do it as a number because, what if n was 4 and L was 0? That would look like 40. right? That doesn't make sense. So we use the letter designation to avoid confusion, because it would be like 52 and stuff. So we got to use the letter designation for L. Remember, L values can be all integers from 0 up to n minus 1. So if we have a specific subshell, for example, let's say we were in the principal quantum number 3. So n would be 3. We just write a 3 there. And let's say it was L equals 0, the S subshell. And you can do 3S like that. I've also seen people do a cursive S, because sometimes people's S looks like a 5. You know what I'm saying? So if you're really good with your S's, then that's fine. If you're not, I'm okay if you use a cursive S. I flip back and forth between the two, because sometimes my S's look like 5s, and I don't want that to look like a 35. Get it? Got it good? So that would be called a 3S subshell. Well, let's say we were in the n equals 6 principal level, right? So n would be 6. And let's say L was 3. So that would be the 6F subshell, right? Pretty easy, right? Very easy. So we get 2 of our, there's going to be 4 quantum numbers. That gives us 2 of them. Now, we'll find out after we're done looking at the orbital, different types of orbitals in each subshell. We're going to look at the m sub L values. So if you want to do a specific orbital, which we very rarely do, you do a subscript here. So you go like 3 or like 6F sub the specific orbital. And we're going to show in this video, what do those specific orbitals look like. We'll look at like a dxz versus a dz squared versus a dx squared minus y squared. They all have particular shapes on how the electron probability distribution is drawn out in 3 dimensions. So if you want to notate a specific orbital, you would go sub x right there. So I'll write that in here real quick. But very, very rarely will you see people do that. All right. So if we do a specific orbital, and again, I'll just write it down, but typically we don't. But if you wanted to, you would do n and then L sub m sub L, right? You do a specific value. For example, let's say we were in the n equals 5 principal energy level, and we were in a p subshell, so L was 0, so we go 5p. And if you remember, there's 3 different p orbitals. There, we'll find out in this one, there's px, py, pz. So let's say it was the z orbital, right? So that would tell you this is the 5th energy level, right? P equals 1, that's the L equals 1 sublevel, so we broke it down, and that's one of the orbitals in that sublevel, one of the 3 particular ones, so 5pz. But we typically don't use that notation, all right? So we just treat the sublevels and put electrons in there later. Let's look at the solutions to the Schrodinger's equation. Again, if the math is too much for you, just ignore it and just know the shapes, which a lot of you probably already do. Let's start with the easiest, the S, then we'll do P, then we'll do D, F. I'll just show you. All right, don't panic. Don't panic. Don't run for the exits. Don't pull the fire alarm, anything like that. This is probably a little more than you did in introductory chemistry, would be my guess. Open up the rabbit hole as much as you'd like. And this, I didn't even open up the whole way. I didn't show you the solutions to this. Not going to. If the math freaks you out, that's fine. Just ignore it and just look at the circles. The when S it's really a sphere. How do you draw a 3-dimensional sphere on a 2-dimensional surface, right? So you're probably familiar, 1s is a sphere and the 2s is a bigger sphere. But I just want to kind of analyze it real quick, looking at the mathematics and why it is. Why is that bigger? And really what it should look like versus the shortcut, things that we draw. Yeah, it's just easier that way. So here, now remember polar coordinates, right? So normally you'd think z, x, and y, that'd be Cartesian. But in polar coordinates, if we're locating, say, that black particle there, with a radius r, see that blue? I kind of squished it on there. Well, if you're going from the z-axis over, that's your theta. That's that angle. You need one angle there. You need the radius. And then if you come down, right, on the xy plane, that other one, and still can't read, I should look that up, what that is. Is that phi or phi? Somebody correct me on that one. That other angle is this angle here. So you've got 2 angles and a radius, and we can locate something with that. what we find in the mathematics for 1s and for 2s, do you see either of those angles in there? We don't. They're independent of the angles, which means they're spheres. Or if you do it in 2 dimensions, it'd be a circle, but in 3 dimensions, they're spheres. Perfectly symmetric all the way around. Okay? That's pretty cool. That's part of really these solutions are 2 parts. The angular portion, the angular electron distribution, and the radial electron distribution, which we kind of talked about with the quantum numbers. So there's no, and this is a combination of 2. You take the radial times the angular, and you get the solutions to Schrodinger's equation. And if you square the wave function, right, if you just get the wave function, it doesn't really have a physical meaning per se for the wave, but if you square it, you get the electron probability distribution in 3 dimensions. So this is the result for hydrogen, right, where Z equals 1. If it was hydrogen-like, there'd be a Z value in there, and you just plug in 2 or 3 or 4, whatever, how many protons there are. Really, we'd have to correct for that. We'll talk about it later. So it's just 1 over pi times 1 over a naught. Remember the Bohr radius? I think that's 53 picometers or something, cubed. And then you've got this exponential decay function, right? E to the negative 2 times the radius over a naught. Since that negative sign's there, as r increases, the electron probability drops. Do you see that? So the electron probability, that term decreases as r increases. So you have more probability closer to the nucleus, and it gets less and less, fades away, kind of like the atmosphere dissipates as you get further away from the surface of the planet, and then just becomes outer space. So it's spherical because there's none of those angles in it, and it gets less probabilistic as it gets further out. So if we drew it like a contour map, the biggest probabilities are closest to the nucleus, and then they get less and less as you get further away. So it looks like a bullseye. It just keeps getting small, like a mountain range. If you look from the top and draw a contour map, and each line represents a particular elevation, each line would represent, like a certain probability. But what we do is we say, well, let's pick the line or the surface that contains 95%, sometimes 90, but we'll go with 95% of the full electron probability and just draw that surface containment. And we'll call that the 1s orbital. Say, do you like that? No, it's a sphere. But that's why it's a sphere, right? Because of the solution to the Schrodinger's equation. Now, if we jump to 2s, the angular thing's exactly the same. There's none of those angles in there, so it's still a sphere. But we get this new, a little bit of the numbers change. But this appears, that wasn't there before. And then this term's a little different. See, that's e to the negative 2r over a naught. This is e to the negative r over a naught. It's not there, right? So this decays slower than this one. See what I'm saying? Which means since the electron probability decays slower, it's bigger. And if you draw a 95% containment curve, it's going to be a bigger sphere than that one because the exponential function. If you love math and you're nerding out in a great way and you're slobbering at the teeth, hey, there you go. If you look at that and go, that's okay. Not important. Just smaller sphere, bigger sphere. Good. That's all I do in intro chem. But look at this term here. What does that mean? 2 minus r over a naught. Would you agree that there's a particular value of radius, distance from the nucleus, where this over this is going to equal 2, and that term will go to 0. That creates a radial node. There's a certain radius, right? So you got maximum electron probability closest to the nucleus, and it decreases as you get further out, and then it goes to 0, and then comes back and then dissipates out. And we draw the 95% containment curve. So we call that a radial node. Oh my goodness, and that happens when r is 2 times the Bohr radius, right? 2 times the Bohr radius cancels out, 2 minus 2 is 0. And when you get a location of 0 probability, that's called a node. Remember from the particle in the box stuff, right? So in 53, so 106 picometers away, you'd get a 0 probability node. That's where it flips. The sign flips too. As r gets bigger, then it becomes negative. It goes from positive to negative. So really a 2s orbital is a 1s orbital with a positive, if you look at the wave function, like positive versus negative, and then it flips at that specific value of r and then goes to 0. So you get this 0 node. And then it becomes negative. So you see, a lot of times you'll see the 2 different colors. That's a little more advanced. Typically, we just draw the whole thing. But realistically, it's a 1s node 2s. And then the 2s orbital contains the 95% probability. So, and then if we did a 3s, we'd get another radial node, and it would be even bigger. But we would just draw a bigger circle to represent our sphere. We good? We good with the s orbitals? It gets worse. That was the easy one, because now with the p's and d's and s, we got to deal. We've only been dealing with r. Now we got to deal with the two angles. No, we're not going to get spheres anymore. All right, so again, I wrote the polar coordinates up there. I'll probably do that every time so you can think about it, where you've got the theta. And I checked that it is phi, phi, both of them. Number of nodes, 4 orbitals. It was different for the particle in the box because the particle in the box had the beginning and end. That goes bye-bye for the orbitals here. So it'll just be n minus 1 or whatever the value of L is, right? So we saw for the 2s orbital, well, 2 minus 1 is 1. We saw 1 radial node, no angular nodes. But it starts getting weird with p orbitals. You'll start to get angular nodes, and as you go from 2p to 3p to 4p, you start to get radial nodes as well. So we know for p orbitals, L is 1. So m sub L values, right? So the angular momentum quantum number is 1, magnetic quantum number -1, 0, +1 gives us 3 orbitals, 3 types. We call it px, py, pz, and I'll show you why we get the 3 orbitals. So let's look at first I want to look at the angular functions and look at why we get these shapes. And then what we'll do is look at the radial function of when they get bigger, why you get nodes as you get bigger. So just remember that. Moving on. All right, let's look at just the angular functions of the 3p orbitals, right? Px, py, pz, and this will be true. The general shape will be exactly the same, whether it's a 2px, 3px, 4px, 5px. They just get bigger and bigger and bigger, all right? But you can see that now they're all 3 over 4, the square root of 3 over 4 pi to start with. That's irrelevant at this point. But for the px, you've got the sine of theta, cosine of phi. I still don't know how to pronounce it. And then for py, it's also sine of theta, but it's the sine of phi, right? So remember, the angle off the z here, that's your theta, and the angle in the xy plane is your phi. And then for the pz, it's the same, but it's just cosine of theta. It's only dependent on that angle, not this angle, which means it's only along the z-axis. Right? So for the pz, you get these 2 lobes that point along the z-axis. For the px, you get 2 lobes pointing along the x-axis. And for py, you get 2 lobes pointing along the y-axis. And as we move on radially, they just get bigger and bigger and bigger. And we'll show that in the next board. So real quick, if you're into the math, don't worry about it if you're not. So let's just say we're in the z-axis here, right? So let's just start at the center, draw a circle, right? And that's the z-axis right there. So let's just take a point along the circle here. So let's call this 0. And as we move along over to here, that would be 90 degrees, or what is that, 1/2 pi? Down here would be pi, and over here would be 3/2 pi, or you can go 90 degrees, 180 degrees, however you like to think about it. But if you're into the cosines and sines, sine, cosine, cosine, sine, cosine, cosine, sine, sine, right? So the cosine of 0, let's just call that 0 here, would be +1, right? So heads up there. Here, the cosine of this is 0. So the probability goes to 0. Here, the cosine is -1, so it goes negative. And here again, the cosine is 0. So you can see in the xy plane, when you plot this along with theta going from 0 to 360 degrees, you end up with this, right? You get a +1 up here, and then it goes to 0, and then to a -1, and back to 0 again, right? Have fun with it. I don't care if you really understand that. But the key is you get an angular node in the xy plane right where the nucleus is, right? Remember, the maximum density for an s orbital is right along the nucleus. There's squat for a p orbital because of the angular node, because of the way it works with the cosines and sines, right? So these are a little more complicated. If you're into it, go for it and see why you get those. Have at it. So let's look at a 2p versus a 3p and show you why we get a radial node as we get bigger, a lot like we did when we went 1s to 2s. All right, so this brings back the nightmares from the 2s, the 1s versus the 2s. So we looked at the angular functions. Those are the same, whether it's a 2p, 3p, 4p, 5p, as long as x, y, z. The shapes are the same. It's just now the size changes. Very similar, you can see from the math, like going from 1s to 2s. So this is the radial function for a 2p, okay? So you get all these constants and stuff over here. But you see the negative r over 2a naught, so it decays over time. So it gets, the radial probability decreases over time, just like for the 1s. So this term goes down over as r increases, not over time. As you get further from the nucleus, the probability of finding it gets lower and lower. And so you end up getting, and because the angulars with all the thetas and phis and stuff, you get, and I could have done x, y, or z, doesn't matter. They look the same, just in a different axes. And so you get the two lobes. And you actually, because of the wave function, you get a positive and negative lobes. If you square it, that information kind of disappears. But we typically draw lobes of two different colors if you want to specify a negative lobe and a positive lobe, which will become important for bonding later. But in general, after you square the wave function, you know, the negative positive termination goes away. And we just draw the 2p orbital like that. That's perfectly fine. That doesn't make sense. Just draw that. You know, so it looks like an hourglass or something. Right? Perfectly fine. Some people say P for propeller. Hey, rock and roll. S for spherical, even though it's sharp. P for propeller, even though it's you know, remember we did sharp, principal, diffuse, fundamental. Let's look at the 3p radial function solution of the Schrodinger's equation. So again, you get a bunch of constants and crap, but you get this term in here, which is what happened with the 2s. See the 4 minus? So there's a specific value of the radius where this term equals 4. 4 minus 4 goes to 0, and the probability the electron goes to 0 creates a radial node. And then this is e to the negative r over 3a naught. This is e to the negative r over 2a naught. So this one decays slower than that one, which means it gets bigger. It's bigger in general. There's more electron density further out. Right? So really what it looks like, you have, for a 3p orbital, you have a 2p orbital that flips into a 3p orbital. So you've got the negative positive lobe, just like this one. But then when you get to that particular value of r, where it goes to 0, and then any value of r later, this term goes negative, and it flips the sign. See? So you go negative to positive. Here you go positive, negative. Weird, weird. Normally we don't worry about that. So what we do is we just draw a 95% containment curve that covers the whole thing, and we don't worry about the signs. And the 3p is just two lobes, but bigger than the 2p. But really there's a radial node. I'll do that in black. There's a radial node right there where the probability goes to 0. And remember, the number of nodes is equal to L, or n minus 1. So here, n is 3. So we get 2 nodes. So you get that radial node there, and you get an angular node on that plane. Over here, n is 2. So you get 1 node. There's no radial nodes, but you get that angular node right there. See how that works out? Hey, rock and roll. I'm not going to do the math for the d orbitals. You're welcome to if you got a week to play around with it, or the f. So I'm just going to show you the different d orbitals and the p orbitals. The f orbitals. We're not going to deal with the f orbitals in this class. We're not going to do lanthanide and actinide chemistry. But the d orbitals next semester you will. For transition metal chemistry, the d orbitals are important. So I want you to know the different d orbitals. So we've got s, only one orbital, and we've got the 3 p's, px, py, pz. Just draw them in different axes. Let's do the d's. All right, for the d orbitals, not going to put the math up there. It's pretty ugly. L is 2, so m sub L values can be negative 2, negative 1, 0, positive 1, positive 2. So we have 5 orbitals. And remember, this starts at n equals 3. You can't get d orbitals until you get to the n equals 3 principal energy level. So you could have 3d, 4d, 5d, 6d, and then there's 5 possible orbitals within it. I want to look at those orbitals real quick. All the angular functions have 2 planar nodes. The p orbitals had 1 planar node, right? With the d ones, we get 2 planar nodes based on the angular functions, all right? And then for every jump in n, so for 3d, you don't have any radial nodes. You just have the 2. So 3 minus 1 would be 2 angular nodes. But if we go to 4d, 4 minus 1 is 3, right? That would be the number of nodes. 2 angular, 1 radial. If we go to 5, we'd have 2, if we had to say the 5D, whichever one it is, we'd have a total of 4 nodes. 5 minus 1 is 4, so we'd have the 2 angular nodes, which stays the same no matter how big it is. 3D to 4D to 5D, the same number of angular nodes. But every time you jump up to another n level, you get another radial node. It's like a 3D within a 4D, within a 5D. It just gets bigger and bigger and bigger. So just subtract 1 from n, and that's the number of nodes that you'll end up with. So let's look at them. I'm just going to draw the 95% shells. That contain 95% of the electron probability. I'm not going to draw like the 3D within the 4D within the 5D, and I'm not going to show all the radial nodes. Okie dokie. Feast your eyes on these 5. Well, if you notice, 4 of them kind of look the same. See the 4 lobes, 4 lobes, 4 lobes, 4 lobes. Has to do with the angular functions. And this is what, for example, 3D would look like. It would look exactly the same for 4D. You just draw them bigger. Right? And then you'd have a radial node in there. But do you see one angular node, a planar node there, and a planar node there? So they each have 2 planar nodes. Kind of weird on this one. It's a little weird. But anyway, the reason I drew them exactly the same, so you can see that for these ones, the dxz, dyz, and dxy and dyz, d orbitals, all have lobes in between the axes. That's going to be very important next semester when we look, we talk, well, anyway, we'll get to it, right? Talk about coordination compounds and complex ions and stuff. We get to 4 lobes. I didn't worry about the signs on this, but notice I changed the axes. So this is the XZ plane, this is the XY plane, and this is the YZ plane. If you draw them all with the same plane, the same axes, then it's harder to draw them in between the axes. It's just, so this way you can distinctly see that the lobes are in between the axes. Pretty cool. Now these two, the dx squared minus y squared and the dz squared, notice that the lobes are along the axes. That's the fundamental difference. Lobes between the axes, lobes along the axes. And these have the weirder notations. So this one, the lobes are along the x and y axes. So you get the d sub x squared minus y squared. That's this notation. For the dz squared, obviously the lobe, now this one's weird. This is the only one that doesn't have 4 lobes. It looks like a p orbital with a donut around it, or like a hula hoop. It's like a p orbital. It's a p orbital along the z-axis with a hula hoop around its waist. Right? See that donut in there? Really weird. I love that's my all-time favorite. I just love that orbital. dz squared. So lobes between axes, lobes along axes. So I would like you to know the different notations. And so you have the m sub l values. -2, -1, 0, +1, +2. But since they're all the same energy, they're all degenerate, we don't really take a specific m sub l value and go, well, that's m sub l -1, and that's m sub l 0. We're not going to go that far for this particular class, so I don't care which one is called what. Right? This could be -2, that could be -2, that could be +1. That's irrelevant at this point. So let's look at the f orbitals. I'm not going to draw all the f orbitals. I'm just going to draw, like here, there's 2 different shapes. There's the 4 lobes, and then the p orbital with the hula hoop, or the donut around its waist. I'm going to do the same thing with f. There's 2 different shapes, but there's 7 total options, 3 of one, 4 of the other. That's all we need, and I'm not going to do the notations. They're pretty gnarly. F for freaky or funky, really fundamental, but anyway, L is 3, so we have 7 values of m sub L, -3 all the way to +3. And really, you can't associate one of those to any one of the orbitals, but we get 7 total orbitals, right? But they don't start till n equals 4, right? To get an L equals 3, you got to have at least an n equals 4. So you can have the 4f, the 5f, the 6f, and they all look exactly the same, just going 4f to 5f. It gets bigger and creates a radial node. Not doing the math. So 4 of the 7 orbitals have shapes that have 8 lobes. They kind of look like this, just oriented, in between along axes. This gets kind of weird. So 4 of them look like these weird flowers, right, with 8 lobes. 3 of the orbitals look like p orbitals with 2 donuts. Or remember the dz squared was a p orbital like with a donut or a hula hoop. This would be like a p orbital with 2 hula hoops, right? Having fun with it. I can't do hula hoops, so we'll do donuts. But yeah, it looks like that. So 3 of them, and obviously one's along the z-axis, one's along the x-axis, and one's along the y-axis with these double donuts. Crazy stuff. So 4 like that, 3 like that. You're good to go, my friends. You've got the s, p, d, and f orbitals. That's all we're going to need. We'll look at orbital energies later when I compare one electron species to multi-electron species, and we're going to show how the sublevel energies change when you start putting more electrons in there. One more quantum number to go. Woo!